We have talked a lot about atoms. Moving into Chapter 3, we will start to look at where atoms come from and how they interact to form new substances. We will start with the origin of atoms. And let's begin with a few questions. We won't answer these right now, but write down your responses and check your answers as they appear throughout the notes. First, how old do you think the atoms in your body are? Next, do you think the number of atoms in the universe is constant, increasing, decreasing, or maybe we don't know this right now? Finally, where do you think the atoms in your body come from? The idea of the Big Bang started out as a joke among physicists, but eventually they determined that it is the most likely theory to be true. Check out the provided video for an interesting summary on the Big Bang. All evidence points to this idea that around 13.8 billion years ago, there was a singularity, and then the Big Bang occurred, and the universe formed, began to expand, and began to cool. Immediately following, there was nothing but elementary particles, such as quarks and electrons, indivisible particles. It was too hot to have atoms, protons, or neutrons, but very soon after, which was about 1 microsecond later, the universe had cooled significantly, and protons and neutrons began to form. Within a few minutes, these began to collide, with enough energy to overcome the electrostatic repulsion, but not enough energy to overcome the strong and weak nuclear forces. So nuclei began to form through the process of fusion. They had about the density of air. There was hydrogen ions, deuterium ions, which is a hydrogen ion with a neutron, helium ions, and lithium ions. For a great number of years, several 100,000 years, the only elements were hydrogen, helium, and lithium. For 400,000 years after that, the temperature continued to drop and the universe continued to expand, and there was no more fusion. Here's a nice illustration of this. It's very hard to represent because there is no outside of the universe, only inside. So what we see here is that right after the Big Bang, there was a lot of activity, and then nothing for a little while. Next, matter began to clump together, and stars started to form, followed by galaxies and planets, etc. The point is that at time equals 0, there were no atoms. However, as atoms started to clump together, after the Big Bang, stars formed and started to coalesce the hydrogen, helium, and lithium into heavier and heavier elements. Remember that atoms of different elements contain differing numbers of protons. So the heavier elements essentially contained higher and higher numbers of protons in the nucleus. One amazing piece of evidence for the Big Bang is that everything in the universe is moving away from us and doing so with increasing speed. We know this because of something called the Doppler effect. For more insight on the Doppler effect, check out the provided video. You can pause this video to watch the provided Doppler effect video now. However, to provide a quick recap, the Doppler effect states that if something is moving towards you, the frequency is higher and the wavelength is shorter. Alternatively, if something is moving away from you, the frequency is lower and the wavelength is longer. We're used to hearing this with sound, but it also happens with light as well. A separate video has been provided for a brief introduction to frequency and wavelength. For the image provided, the person on the right likely hears the motorcycle at a higher pitch than the person on the left, since the motorcycle is moving towards the person on the right. So they'll hear the motorcycle at a higher frequency and a shorter wavelength than the person on the left. Although we experience the Doppler effect most commonly through sound waves, the Doppler effect applies to all waves. Astronomers can use the Doppler effect to study stars through a phenomenon called the redshift. One of the reasons that we know what things are in space is because we can observe the light spectra of these objects. A spectrum is a representation of all the colors emitted from an object. You can imagine a rainbow as a spectrum that results from the sun's rays passing through water in the atmosphere. See how the light of the sun is dispersed into an array of colors? We can look at the spectra of stars to look for absorption lines. These absorption lines tell us what frequencies of light are absorbed by the outer atmosphere of the star we are looking at. For example, here is the absorption spectrum for the sun. Notice that several frequencies are absorbed, or not visible in the spectrum. Depending on the elements present in our sun, different frequencies will be visible. We can compare that to the absorption spectrum from a supercluster of galaxies 1 billion light years away. Notice how the absorption lines are the same, but all of the lines are redshifted. All of the lines are shifted towards the red end of the spectrum. With a little calculation, we can figure out how far away things are and how fast they are moving by comparing their spectra. The spectra of elements are more redshifted the farther away that they are. Let's go back. Remember, everything in the universe is moving away from us with increasing speed. It is not because we are the center of the universe, because we aren't, but because everything is moving away from everything else. As evidence, we can recognize that the spectra of all other stars and galaxies are redshifted. If everything is redshifted, that means the universe must be expanding. Keeping in mind that the universe is expanding, if we were able to rewind time, the universe would contract. The farther back in time we go, the smaller the universe becomes. At some point, it would shrink so much that it would be a single point containing all the matter and energy of the universe. It would be extremely dense. This point, or singularity, was infinitely hot 13.8 billion years ago at the time of the Big Bang, when all the matter in the universe was created. What other evidence do we have for the Big Bang, though? Well, first, we can see that the universe is expanding from the redshift, but there is also evidence from computer models to support the Big Bang theory. And additionally, we can observe the cosmic background microwave radiation. This cosmic background microwave radiation is almost perfectly uniform. It comes from the early universe and is a faint glow of radiation from when the universe was hot, dense, and consisted of plasma of hydrogen nuclei and electromagnetic radiation. This is an image of the background radiation of the universe. You can see that the radiation is clumpy. This allowed matter to clump together and things like us to form. The image shows the temperature of the microwave radiation that is almost evenly distributed across the universe. Tiny differences in temperature, microdegrees on a 3 Kelvin background, show up as different colors. Red is hot and blue is cold. These differences allowed matter to begin to clump together, and as matter clumps together, gravitational forces take over, the temperature rises, and nuclear fusion begins.